Now let's take a look at the second part of our example where we've added the emitter resistor to our amplifier circuit. So in part B, we still want to find our small signal voltage gain, and the only difference in our circuit is we've added in this emitter resistor with a value of 0.6 k ohms or 600 ohms. Everything else is the same. So just like with our previous part A, the first step would be to do DC analysis. And because we've added that emitter resistor, we're going to have slightly different values. This is shown as supplement on page 4-20. We're not going to go through it here, but the end result is that our ICQ is now going to be equal to approximately 0.418 milliamps. So we see that that's changed a fair amount. We want to use that ICQ value, or our Q point location, to get our small signal hybrid pi parameters of R pi and GM. So our R pi is VT times beta over ICQ, plugging in our values. And so I glossed over this, but we assume, of course, this is the same transistor as before, so we still have the same beta, VBE on, and VA. And so this gives us a value of approximately, if we assume room temperature, our VT is 26 millivolts or 0.026 volts. Our beta, as given in the previous video, was 120, and our ICQ is 0.418 milliamps. So plugging all of that in, we get approximately 7.464 k ohms for our diffusion resistance R pi. So we also need our GM, which is equal to ICQ over VT. Plugging in our ICQ of 0.418 milliamps, we divide that by our 0.026 volts, where we again have assumed room temperature, and that is approximately equal to 16.077 milliamps per volt for our small signal transconductance. Now, what we're going to do now is just go back and use our previous AC analysis. So we're not going to go through our small signal circuit analysis again. We don't need to. It's the same configuration we saw before, so therefore we already have an equation for it. If we had a different configuration, then we would need to redo that analysis. So if you are curious where that is in the notes, you can look on pages 4-16 and 4-17. Or just the same equation that we had a couple videos previous. And so in this equation of interest is our RIB. And so remember, our RIB we defined as R pi plus 1 plus beta times RE. So that was our resistance reflection rule. Plugging in our values, this is approximately 7.464 k ohms plus 121 times our 0.6 k ohms. And so what we're going to see is that, again, even though this RE value is relatively small, because it's multiplied by that 1 plus beta, it's going to essentially be dominating that RIB. So we get that this RIB is then plugging in those values approximately equal to 80.064 k ohms. All right, and then we also need to know our input resistance Ri, which remember is defined as R1, R2, RIB. And what we're going to see is because our RIB is larger, this Ri, our input resistance, isn't going to be as small. So again, we have our R1 of 250K, our R2 of 75K. Our RIB is now sort of on par with these two resistors. So if we calculate that parallel combination, we get that it's approximately 33.531 k ohms. All right, so using again this previous AC analysis, we had that our gain equation is equal to negative beta times RC divided by R pi plus 1 plus beta times RE. And then all of that was multiplied by RI divided by RI plus RS. And so, of course, keep in mind that this whole term here in the denominator is just RIB, which we've already calculated. So we can say this is approximately equal to, so we have negative beta, so negative 120. Our RC is 5.6 k ohms. Our RIB was 80.064 k ohms. And then this voltage divider ratio, we have 33.531 for our RI So 33.531 again for our RI, and then our RS is 0.5. Okay, so if we evaluate that, we get that our voltage gain, our small signal voltage gain, is approximately negative 8.270. And so we see that, as expected, this is much smaller than the previous value we had, which was around negative 170. So much smaller than with no emitter resistor RE. But, of course, our advantage of using this configuration is that it should be more stable against changes in beta. So if we consider those same beta changes we did previously, so let's say it's plus or minus 50%, so we start at 120, minus 50% would put us at 60, plus 50% would put us at 180. So if we were to go through that analysis again and recalculate our AV, so first of all, we had negative 8.270. What we would find is for a beta of 60, we have negative 7.838, and for 180, we have negative 8.424. So we see we have much better sensitivity, so much better, and so by better, I of course mean lower sensitivity. Sensitivity to our changes in beta, but we have reduced gain. So again, this sort of all goes back to this idea of trade-offs in our design. One other thing to note too is now as we have changes in beta, we're going to be changing more parameters. So changes in beta means we're going to have changes in our IBQ. So we didn't show that explicitly, but our IBQ from the DC analysis, our ICQ, our RPi, our GM, our RIB, and our RI. So all of these values are going to be affected as we're changing our beta. But ultimately, as we see here, we're going to have much smaller changes in our AV as we have changes in that beta parameter. One other thing I want to note briefly is earlier in the notes when we were looking at this configuration, we said that we can make an approximation of our small signal voltage gain of negative RC over RE. And so let's see what that gives us for this circuit, and let's see how good of an approximation it is. So we have 5.6K for RC and 0.6K for RE. So if we plug those values in, we have negative 5.6 over 0.6, and that gives us negative 9.3 repeating. And so of course, if we compare this to our negative 8.27, we can see it's obviously not super close, but again, it could be a decent first order approximation. So good first order approximation. And one thing we can note too, which is always going to be true, is that this approximation down here is going to tend to overestimate just based on how we're making assumptions and what types of things we're assuming. So again, good first approximation. It can kind of give you a ballpark idea of what your design is going to be, but you want to go through that more rigorous analysis and or use simulation to get a more accurate picture.